Reaction quotient. This is another quite important part of chemical equilibrium, and in my opinion, it's the easiest one to be understood and to be learned. Before we're going to look at several examples, let's get to know what does it mean by reaction quotient first. So basically, when we want to write the reaction quotient expression, it will be the same as the way we write Kc or Kp. If you look at the general equilibrium equation on top over here, and the way we're going to write the Q expression, for example, for the Qc, it is exactly the same as the way we write Kc for this reaction on top. If you look, that part is for the product with to the power of C for concentration C to the power of D for concentration D. Exactly the same as the way we write Kc. And the bottom bit right there is corresponding to the reactant side. Same goes to how you're going to write Qp. So what is the difference now between Kc, Kp, Qc, and Qp? The difference is right over here. The reaction quotient Q may not necessarily at equilibrium states. The value that you're going to plug into here and you're going to plug into here, concentration and partial pressure for Q, reaction quotient, may not necessarily at the equilibrium states, unlike for Kc and Kp. For Kc and Kp, we need to find out what are the values at equilibrium. Then we will be able to solve or to get the value for Kc and Kp. So these two over here, they will use concentration and pressure at equilibrium. That's why when you want to find Kc and Kp, you need to have the ICE table. Okay? So when we say that, you can imagine now, when we try to work out the value for Qc and Qp, ICE table will not going to be necessary. So we're going to look at a few examples later on, and you will see that ICE table will not going to be used for finding the value for Qc and Qp. So that is the major difference. So what is the purpose of finding Q? Why do we need to find Q then? The purpose is, in exams, you need to find Q because you have to compare with the equilibrium reactions K value, just like how we talked about in the beginning. The questions will give you a situation, they will give you a set of data, and you're going to use that data. You're going to write down the Qc or Qp expression, and when you get the value for Q, you need to compare with the K value. After you have done the comparison, from that comparison, we would be able to know the direction of the reaction in achieving equilibrium. So that is the purpose for us to learn how to write reaction quotient Q to compare with the value of K. And after you have done the comparison, then you would be able to know the direction of the reaction in getting the equilibrium. There are three situations that you might gonna encounter when you solve the problem about QC, QP comparing with KC and KP. Let's have a look at the first one on top over here. So when you have the value of Q bigger than K, where does the reaction move? Is it to the left-hand side or is it to the right-hand side? To understand this better, it's better for us to visualize the situation in terms of a range over here. The value can have between 0 and infinity. So let's imagine that way. So when you have Q value bigger than K, you can imagine now the K value will closer to 0 and Q value will be closer to infinity. Now, before I'm going to proceed, you have to understand that infinity is a huge number. It's a big, big, big number. Therefore, when you are bigger in value, you would be closer to infinity. And K over here, since it is going to be smaller, it will be closer to 0. So I'm going to put K. Let's say we're going to put K value right over there. So when you have K at that position, your Q would be closer to infinity. Let's say right there. I'm just going to put it there. So in order for you to achieve equilibrium, K, remember, K is equilibrium constant expression. Remember, K is equilibrium. You have the word constant expression. So when you have the word constant over here, that means K value is the one that will stay. K value is the one that will be staying there. It will not going to change unless you're going to change the temperature. Yes, K can change. But assuming that the temperature does not change, in order for you to get Q to be equivalent to K, the reaction needs to move. Okay? So when you look at the value of Q over here, which is bigger than K, where does the reaction will move? Yes, the reaction will surely going to be shifting to your left. Okay, so it will shift to the left. When the reaction is shifting to the left, that means the reaction needs to produce more reactants in order to achieve the K value. Okay? So the conclusion over here, what you can write is, when Q is bigger than K, the reaction shifts to the left. Okay, to the left. To the left in brackets, to the reactant side in order to achieve Q equals to K. So in brackets, equilibrium. Okay. So what about this one then? The one at the bottom over here. Now I think you can guess what's going to happen to when Q equals to K. When Q equals to K, that means no shifting because equilibrium has been achieved. So when the value of Q is equals to K, you don't have shifting because equilibrium has been achieved. So that means Q is the same as K. So in the situation of Q smaller than K, that means your K value will be closer to infinity. Q value will be closer to 0. So maybe Q is going to be right here. Okay. And then K is right there. So to get K value, your reaction must shift to the right. Therefore, the reaction shifts to the right. Okay, shifts to the right to the product side in order to achieve Q equals to K in brackets equilibrium. Okay, so those are the three situations in reaction quotient when you compare that with K. Now let's try a few examples. So when you read the question and you try to find out what the question wants, it is obvious that the question wants you to find the value of Q and compare it with the Kc value of this reaction on top. From what the question wants is the reaction at equilibrium. So the question wants you to identify whether the reaction is at equilibrium. And it states further, if not, in which direction is it progressing? Is it to the left? Is it to the right? Okay? It's obvious. This is the question wants. So when you read the question, when you know that the question wants you to predict the direction of the reaction, at this point, you don't have to worry about ICE table. You don't have to construct ICE table. But what you need to do is, you need to write the QC expression. Okay, for this, because you want to do this. Okay. So what we can do, notes over here. No need ICE table. Okay, we don't have to construct ICE because we want to compare Q and K. But what you need to do now is comparing QC and Kc, like what you have in there. You have value of Kc, and you want to compare with Qc. We have discussed just now the Qc expression. It's important for you to write it. For concentration would be concentration of NO2 to the power of 2 over concentration of N2O4. In exams, by writing your QC correctly, you will get 1 mark. So plug in all the values that is given to you. Question gives you concentration of N2O4 and concentration of NO2. So we're just going to plug in that into your expression. So QC, when you have the value of QC, you have 0.55 to the power of 2. Okay, so NO2, 0.55. Okay, NO2, 0.55, substitutes to the power of 2. And then N2O4, 0.12. So you're going to put that down there. 0.12. And the value of QC would be 2.5. So you have found the value of QC. You will get another 1 mark. Now we need to compare. Now, your QC value, is it bigger or is it smaller than KC? Look at your KC. KC is 0.21. This is 2.5. So if you're going to visualize that with this one, this range just now, your QC is about here. QC maybe about there, 2.5. And then your KC is right there, 0.21. So where do you think it will shift? It will surely shift to the left to get the value of equilibrium constant expression concentration. So value of QC is indeed, QC is bigger than the KC. So when you write this, by writing this, you get another 1 mark. But we're not going to stop right over there. We have to write a conclusion. So the conclusion that we're going to write is, since QC is bigger than KC, the reaction shifts to the left, in brackets, reactant side, to achieve QC equals to KC in brackets, equilibrium. So meaning to say, when you shift to the left, this reaction needs to make more of N2O4 in order for the reaction to achieve the KC. Okay? So with that conclusion, you will get another 1 mark. Okay, so let's try another example. So right here, do we need to use ICE table? So that's the question. Again, if you are asked to compare Q and K, you do not have to construct the ICE table. So let's analyze the question a little before we're going to decide. So I like to look at what the question wants first, then I will have the idea of what I need to do. When you look at what's the question wants, it says here, initially, is the mixture already in chemical equilibrium? So the question wants you to help the reaction to know whether it is already at equilibrium. In this case, in this kind of clue that you have, if you have clues like this, they ask you whether it is going to be at equilibrium, and then you have value of Kc or Kp given to you. That means you don't have to construct ICE, but you need to compare Qc and Kc. Okay, so because you need to find something at equilibrium, we have to compare Qc and Kc. So this is what we need to do, because the question wants you to find out whether the chemical equilibrium has been achieved or otherwise. When you want to compare Qc and Kc, no need ICE table, okay? So the first thing you need to do is write the Qc expression. So the Qc expression, since we're working with concentration, it will be in terms of concentration. First is this one, Hi, okay, product, concentration of Hi to the power of 2 over concentration of H2 times concentration of I2. Okay? So by writing that correctly, you will get 1 mark. But when you read the question now, it gives you in terms of mole. You have 0.040 mole of Hi, you have 0.010 mole of H2, and 0.030 mole of I2. Therefore, we cannot take these values directly and plug them into your Qc expression. What we need to do now, we need to convert this value in terms of mole into concentration. And that should be easy because the volume of the vessel is given to you. Okay, we have the volume of the vessel. Therefore, we can use those mole over there to convert that into concentration. Okay, so the concentration for H2 is about this 0.010 over 2.0. Okay, so that one would be 5.0 times 10 to the power of -3 molarity. And then we have concentration of I2. So I2 is right here, 0.030 mole over 2.0. Then we have 0.030 divided by 2.0. We have 0.015 molar. And next is the concentration for HI. So we have 0.040 divided by 2.0. We will have 0.02 molar. Now, after we have got all the concentrations for all of the species involved in this reversible reactions, we can take all of these values for concentration and substitute into your QC expression. When you substitute into your QC expression, you will have to do the same thing like what we have done just now. We're going to compare with the value of Kc. In the case of this question, the value of Kc would be 54. So when we substitute the value, the QC value, you would get 0.020 to the power of 2 divided by 5.0 times 10 to the power of negative 3 times 0.015. If you want to double check, HI 0.02 to the power of 2. Yes. And then H2, 5.0 exponent negative 3 times with I2 concentration, which is 0.015. And that is correct. And the QC value would be 5.33. The value of Kc is 54.0. Obviously, we have a value of Kc way bigger than Qc. So if you imagine that you have this range, okay, your Qc would be somewhere around here, which is 5.33. And your Kc would be somewhere there, 54.0. So where do we go to get your equilibrium? The reaction for sure would shift to the right. So Qc is smaller than Kc. You get 1 mark for that, 1 mark for that one. So how do you write the conclusion? Qc, therefore, the reaction shifts to the, remember, to the right. Okay, because Qc is smaller than Kc, so to the right. In brackets, in order to achieve Qc equals to Kc, in brackets, equilibrium. Okay? So next question, let's have a look at this one. Over here it gives you the value of Kp for the reversible reactions we have when the 2NOBr gas decomposes to form 2 mole of NO gas and bromine gas. So in the experiment, each of the component, which is NOBr, NO, and Br2 gas, is at 0.10 atmospheric pressure. Is the system at equilibrium? So when you look at the key word or what the question wants you to find out whether the system is at equilibrium. So when you look at this kind of question, automatically we can know that what we need to do is to compare Qp with the given Kp. When we need to compare Q and K, we don't have to construct your ICE table. And the first thing we need to do is, of course, we need to write down the Qp expression first. So we have partial pressure of NO to the power of 2 times with partial pressure of bromine gas over partial pressure of NOBr to the power of 2. And by writing that down correctly, you get 1 mark. Don't forget to write your P over here because it can be QC or QP depending on the situation given. By substituting all the value inside QP, you would get 0.10 to the power of 2 times 0.10 over 0.10 to the power of 2, and you would get the value of Qp equals to 0.10. Now, when we look at this value for your Qp, is it going to be bigger or smaller than the Kp? Again, we can visualize that with this range here. As you can see, your Qp is 0.10, Kp is 60.6. Therefore, your Kp would be closer to your infinity, and your Qp would be closer to, so Qp is right over here, would be closer to 0. Thus, the shifting will go towards the right hand side. Okay, so you're going to be producing more of your products. So what we have over here is your Qp is smaller than Kp. So in the example just now, we have looked at Qp value is smaller than Kp. Therefore, the system is not at equilibrium. So what will happen then? The system or reaction shifts to the right, to the product side, to achieve Qp equals to KP in brackets equilibrium.